give us a talk on meta-analysis. Before I introduce him, let me mention a few housekeeping issues. We continue extending CME credits for our Tech Talks and our ID series presentations. We'll distribute the information via email to those who are registered for today's event. If you did not register prior to today's talk, you can still obtain the CME code from Deborah Reese, and her email address will be posted in the chat. Upcoming events, October 28th, ID series on food security and stigma. And November 6th is the next Tech Talk on how AI and data science are being implemented at Christiana Care, some case studies. So please mute your audio during the talk unless you intend to say something or ask a question. Dr. Zhang is Director of Biostatistics here at the Institute for Research on Equity and Community Health, IREACH, at Christiana Care. He's an affiliated professor of statistics in the Department of Mechanical Engineering at the University of Delaware, and adjunct faculty at Thomas Jefferson. He is a fellow of the American Heart Association. He received his master's degree from the University of Arizona and the PhD from the University of Iowa. Zugui has been a member of the Delaware Economic and Financial Advisory Council on Healthcare Spending Benchmark Subcommittee since 2019. He has taught multiple courses in biostatistics, from basic to advanced, here at Christiana, to medical residents and fellows. He has a long list of publications and has been funded as a co-investigator on multiple grants. And of course, he's a member of our Biostatistics, Epidemiology, and Research Design Corps for the Delaware CTR ACCEL. Zugui, go ahead.
Thank you very much, Rick, for your very nice introduction. Today, I'm going to talk about metadata analysis as an introduction. In today's presentation, I'm going to talk about systematic reviews and metadata analysis with some basic concepts, focus on practice and reporting standards. For the detail, I'm going to talk about core effect sizes in metadata analysis, focusing on forest follow plots, bias, publication bias, heterogeneity, such as the heterogeneity measurement matrix like Q, I square, tau square, and others. Also, I'm going to talk about some techniques in sensitive analysis in metadata analysis. Why do we need to conduct metadata analysis? Metadata analysis can be considered as a synthetic evidence to pull the results across multiple studies to provide more precise estimates, which means we combine some studies to provide more precise estimates to increase power, detect the effects that the individual studies may be underpowered. And also we want to generalize the results from multiple studies, so the generalizability to integrate evidence across different populations, settings, and methods. One of the important things in metadata analysis is to explore heterogeneity, which is to quantify and explain variability in effect size by using some measurements such as I square, tau square. In the analysis, another objective is to identify bias, to highlight publication bias or small study effects by looking at follow plots and corresponding tests. Eventually, our metadata analysis results will be used to guide decisions like inform guidelines, policy, and practice with stronger cumulative evidence. So those are the reasons why we need to conduct metadata analysis. If we read any paper related to metadata analysis, usually is the paper said a systematic review and metadata analysis. So here we have two concepts, systematic review and metadata analysis. This can be considered two separate tasks, but highly related. Systematic review is a constructed reproductive synthesis of evidence, like for the predefined questions, protocols, and others. Metadata analysis is another way, can be considered a part of statistical analysis. This is a statistical polling of comparable quantitative results. So usually we combine together systematic review and metadata analysis. The benefits we can obtain from the analysis is to increase the precision, as we just pointed out, power to detect effects, and to explore the heterogeneity. But we have to be aware of some risks, such as if our analysis, specifically our studies, including analysis, are not so well, that could be in danger of garbage in, garbage out. Maybe we can amplify, we can make the bias even worse without like appropriate methods. When we conduct the metadata analysis, we usually see a abbreviation called PICO. This is stand for population intervention comparator and outcomes. So our metadata analysis uses like a PICO to stand for what our working resources. In recent years, we have several public accessible tools or protocols for the metadata analysis, like Prospero, which is an international systematic review register that prospectively registers systematic review protocols, creates publicly available registration records, and issues a unique registration number for each registered review protocol. When we conduct analysis in metadata, we have like a specified primary, secondary outcomes, and look at the time points, effect size matrices as well. When we conduct metadata analysis, the basic and the fundamental work is to search the important studies. For the search strategy and study selection, we can, in our healthcare, we can use like Medline and other medical related databases. We look at document strengths, data limits, language restrictions, and deduplications. Also, we will look at the dual independent screenings or other things. So this provides us a resources for us to connect related studies in metadata analysis. Here is the way we should carefully consider how to connect our data. Data here is previous studies, which means we should have a checklist before polling. Are populations, interventions, comparators, and outcomes PICO sufficiently similar? Are outcomes, definitions, time points aligned or transferable? Is the risk bias acceptable for combining? So this is the list that we should check before we conduct collecting data before polling. Specifically, if we could identify the studies in terms of study type, we can differentiate two types of studies. One is the randomized trials. Currently, we use like ROB2 This is for the revised tool developed to assess the risk of bias in randomized controlled trials. So for the RCTs, so ROB2 is for randomized trial. We have another specific tool for observational studies, Robbins-1. This is for the risk of bias in non-randomized studies of interventions. And of course, in our studies, sometimes we use just a combination with random with RCTs and observational studies. So we can like try the comprehensive method. After we select our studies and then we identify what kind of tools we are going to use. After that, we can do like the actual data extraction. We can build pilot formats, extract like study design, arm sizes, events, means, outcomes, like standard deviation, and so on, and follow up. Perform intention to treat dominators, capture adjusted versus unadjusted. Here we use ITT, which means we get the information from based upon the intention to treat. When needed, we can convert medians or other statistic outcomes to like a standard way. Currently, we have a guideline for conducting metadata analysis, which is Prisma, which developed first in 2009, which is the preferred reporting items for systematic reviews and metadata analysis. This is a widely used tool in healthcare, social science, and political research. The purpose of Prisma is to improve transparency, reproductivity, and completeness in reporting, systematic review, and also the guideline for the metadata analysis. First published in 2009, and then widely endorsed by many journals, publishers, and researchers, specifically in healthcare. Since 2009, systematic review methods and evidence synthetic have advanced. So in 2020, about 5 years ago, Prisma updated reflects the methodological and the technology progress. And currently, Prisma 2020 is the international standard for reporting systematic review. In Prisma 2020, they consists of 27 item checklist, including guidance on title, abstract, introduction, methods, results, discussion, funding. They have a flow diagram. They have expanded guideline. Also, they have some like flexibility about our complex reviews of interventions, diagnostics, and others. The key items include like this is also the guideline for us to connect the information or connect the data for metadata analysis, including title, abstract, introduction, methods. The main part in metadata analysis is about the results, study selection, study characteristics, number of patients, risk of bias, results of synthesis, certainty of evidence. The other items such as discussion, others are also included in the checklist. Here is the flow diagram for systematic review. As we can see, we have the previous studies, identification of new studies or databases and registers, identification of new studies or other methods. And here they have like the included screening, identification with each part. So this is the flow diagram. Now, after we connect the data we will consider like effect size. For effect size, we will have for the different type of outcomes, for continuous, for binary, and for the time to event. First, for the continuous, we will look at the mean difference, such as like the two group outcomes. We will get the information about intervention group mean or experimental mean and the control mean. We get the mean difference with the variance, and also we get the standardized mean differences. Here, standardized mean differences used when studies measure the same construct on different scales. So when we collect the data, we should make sure if like the outcome is in the different scales. So for example, for BMI, sometimes we just use like the BMI based on the formula, but sometimes we may use the Z-score to standardize the BMI. So we need to make sure they are in the same scale. Otherwise, we need to use the standardized mean difference. For the odds ratio, which is related to binary outcomes, we have like the odds ratio variance, and then we can forecast this effect size. For the survival data analysis, we should connect the results based upon the hazard ratio. If hazard ratio not reported, we need to reconstruct the log of the hazard ratio and the standard errors from published confidence interval log rank statistic or survival curves. The plot with fixed or random effects as with like odds ratio or mean difference. When we connect the data from data to poor effect, the basic framework is first for the study level data, we will connect the data for the continuous, for the binary, time to event, and then we compute effect size. After the effect size, for the each type of outcomes, continuous, binary, or hazard ratio, we will have the model for metadata analysis, and then we will work on the metadata analysis with a fixed effect and a random effect. After that, we will get the plot estimates about the outcome, and also we have statistics about the heterogeneity matrices, which I will talk about in more detail. After that, we will have the metadata analysis is specific outcomes or figures. Those are forest plots and follow plots. So this is the metadata analysis framework from data to plot effect. So when we do the analysis, we should choose the appropriate effect size in metadata analysis. Like for the continuous outcomes, we use the mean difference, and if scales different, we should use the standardized mean difference. For the binary outcomes, such as like mortality, treatment success, or adverse events, we use the odds ratio and as the main part. For the binary outcome, the alternative outcomes also include like risk ratios, risk difference, and others. For survival analysis, we will use time to event outcomes, including hazard ratios. If hazard ratios not available in the publication in the papers, we could use like the log of this corresponding information. As we know that generally speaking, we will choose the different data type outcomes for continuous, binary, and survival time to event. This is the comparison of effect sizes in metadata analysis. As we can see for the different type of effect size, we have different data type, the formula, and the interpretation or how to use it. Here, I listed the continuous, binary, and survival outcomes. With the continuous outcomes on the same scale, continuous outcomes on different scale, binary outcomes, time to event. So this is the effect size in metadata analysis for different type of outcomes. As we can see, this is the way how we can do the from data type to effect size, continuous, mean, difference in means, binary, log odds ratio to relative odds of event, time to event outcomes, log odds ratio, relative hazard of event over time. Here is this data type to effect size with formula. I think this can be considered as the outline for us to get the statistical analysis plan in metadata analysis. This is the specific summary for the metadata analysis in effect size. Now let's move on to how we can conduct metadata analysis. First, we have a general metadata regression. This is a model about the parameter related to studies. And here, this theta hat is for mean difference, for log odds ratio, and for log hazard ratio. So that we can use a pseudo linear regression model to model the metadata analysis. For the mean difference, we can just use the theta hat mean for the linear combination, but for the binary and the survival analysis, this linear type metadata regression formula we need to do for the log transformation. And here we have two parts. For the linear parts without error term, this is like the fixed effects. And for the error term, implicit I, we have this random effects term. So we use the random effects meta regression, pre-specify and limit the number of moderators to reduce multiple testing risk. We can center and scale continuous moderators, report residual heterogeneity, tau square, and the pseudo R squared to measure the fitness of this model. So this is our metadata regression model. As I just said, we have two parts. Like this fixed effect is the common true effect. We can weight with the 1 over the variance of the theta hat. And for the random effects, we look at the distribution of true effects between studies variance tau squared. So this is the reason why the tau squared can be used to measure the variability of the studies. And here the interpretations could be different, like the mean effect and the conditional common effects. So this is like the very important part in metadata analysis. We will look at the fixed effect and the random effects. From this metadata regression model, we can have the statistic to estimate between study variance, tau square and I square, which is the measurement about heterogeneity. Why heterogeneity matters? Because we need to estimate the impact of different studies on the overall outcomes. So heterogeneity is one of the key concepts in metadata analysis, measured by Q, tau square, and I square. We have the cohort Q with the degree of freedom, and the K here stands for the number of studies included in the analysis. I square is the max value for this statistics. The I square can be considered as a proportion of variability due to heterogeneity. Generally speaking, I square use a random effects model. And the tau square here, the variance of true effects, tau interpreted on effect size scale. We use the estimators to get those heterogeneity measurements. And we can consider the different estimators specifically when the number of studies included in the metadata is small. How small is small? Usually like 5 or less than 10. We can consider like the K is small. We should use some alternative or just the formula to estimate this heterogeneity. After we get this, we can get the prediction interval for our estimate. Here, I provided 95% prediction interval for new studies, true effect, and random effects. The prediction interval complements confidence interval is crucial for clinical applicationicity. As I said, forest plots and follow plots are the important outcomes in metadata analysis that provides a visualized study effects with the confidence interval, weight contributions, and pooled estimates. So we also can check for outliers, influential studies. Yeah, for this first class, we will see the first class soon. Follow plots are usually used for the publication bias. Follow plots, symmetry or large symmetry and symmetry, we use the contour enhanced follow help and visual curves for symmetry. Visualization is a good way, but in statistics, visualization is always not enough. So we have a specific test for the publication bias, which is Eagle's test. So we will use like this statistical confirmation for bias. And for the nonlinear trim and fill sensitivity, P-curve or selection models for robustness. So that also can be used to look at the publication bias. For the different type, since we have the different effect size, so hello. For the metadata analysis, now I'm going to talk about the different outcomes type. First is for the continuous, which is the rate of change. So this is the metadata analysis applied to mean differences. We compute a mean difference or HGSG with bias correction. We interpret standard mean difference in similar units by standard deviation benchmarks or medical important difference, back translation, or the minimum important distance. And we will look at the pre and the post intervention measures. We calculate mean differences and the corresponding 95% confidence interval. Here is this. Here is the forest plot for continuous outcomes, and we have mean and standard deviation from 7 studies, and we look at the hospital length of stay. In this first plot, we can see in the left side, the first left side, the lower, upper part is related to this studies summary from the different studies. And then the left side, upper right side, is the corresponding mean difference and the corresponding 95% confidence interval, provide the weight for the common effect or the fixed effect and the random effect. So this upper part is basically the visualization of results for different studies included in the dataset. And then in the lower part are the outcome for metadata analysis. They provide us the common effect model with the sample size and also with the mean difference, corresponding 95% confidence interval, and about the common and the random. And then they will provide us the random effect models results. Also, they use the first plot providing the common effect models results and the random effect model results, as well as the heterogeneity, I square, tau square, and the corresponding p-value. So this is the first plot for continuous outcomes. Here, this is an example for the hospital length of stay. For the binary, we put a log odds ratio with residual estimate, maximum likelihood, and others. Report tau square, I square, and the corresponding the 95% confidence interval. So here we include about 12 studies with outcome odds ratio. The upper part is the summary, the visualization, and the numerical summary for each study. The bottom and the lower part is the common effect model, random effect model, with this odds ratio for common effect model and odds ratio for random effect model. So usually we will report this common effect model and the random effect model as a results for the metadata analysis. Similarly, we have the heterogeneity, I square, tau square, and corresponding p-value. Here is the formal plot to indicate the distribution of studies. Here we use the different color to indicate each study's results with p-value less than 0.01, less than 0.05, and less than 0.1. And then based upon this formal plot, we can see if this study distribution evenly or systematically, and then we will see this white part for the publication bias. So here is the test of plot or photo plot as the symmetry. We conducted the Eagle test, and then we get the corresponding t-value, degree of freedom, p-value, and then so for this one to indicate the results. Now let's move on to time to event, which is the survival data analysis. This is a metadata analysis consists of about 9 or 10 studies with the hazard ratio reported in each study and the corresponding lower limit and the upper limit for the hazard ratio. So we will convert to a log hazard ratio and the corresponding standard error and confidence interval. So we run the random effect meta-analysis. So when we conduct a metadata analysis for survival outcomes, we need to do this transformation. And then we will focus on the forest plot and the furlough plot generated the outcomes. So first, we generated the forest plot for hazard ratio, which is for the survival analysis, and we get this common effect models hazard ratio. We get the hazard ratios for random effects model and the corresponding 95% confidence interval. Also, this first model provides us the I-square and the tau-square for this survival analysis. As we can see, for the time to event metadata analysis, the common effect model with a hazard ratio 0.96 with p-value 0.43, and the random effect model with hazard ratio 0.93, the p-value 0.39. And also we get the heterogeneity measurements about Q, tau square, and I-square here. So based upon those time to event metadata results, we can interpret that no strong evidence of treatment effects because we see the p-value is greater than 0.05. And here we see the heterogeneity with I-square 62%. We also see like the p-value 0.03, so we can conclude that we observe the moderate heterogeneity among those studies. And here we can use the counter-enhanced follow plot to further look at like this publication bias. If we look at the dark gray area, medium gray area, light gray area, and then we can, if we see the white area, we can conclude that they could have like a possible publication bias. And also, when we conduct this ego test, we see p-value is 0.02. We conclude we have like potential small study effects. Yeah, so here is the Eagles test. As I mentioned that for the furlough plot is just a visualization. For the publication bias, we should conduct a statistical test. Here is the Eagles test. In R for Eagles test, usually they will set up the k-value default is 10 or larger. If our number of studies is less than 10, we should specify the k number to like 5 or even as small as 3. Based upon this Eagles test, we can interpret statistically significant asymmetry, which is p-value less than 0.05, suggests a potential small study effects or reporting bias. So because our study only consists of 9 studies, so we should be careful about our interpretation, which means we should be interpreted with caution and limited by only 9 studies. After we conduct metadata analysis, we should also further conduct sensitivity analysis because it is possible our our cumulative studies may be impacted by some important studies, either with a very large sample size or with a very small sample size. We want to look at the influence diagnosis. And so that we could exclude high risk or bias studies or small sample thresholds. So this is the reason why we should conduct a sensitivity analysis in metadata analysis. Here, I'm going to talk about three popular sensitivity analysis in metadata sensitivity analysis when we look at the metadata. First is about leave one out analysis, which is used for the influence diagnostics. The purpose is to assess robustness by removing one study at a time. So for the odds ratio studies, I just mentioned a few minutes ago, I conducted the leave one out analysis. The null hypothesis is that excluding any single study does not substantially change the overall effect. And then I ran the leave one out analysis. Here is the results. As you can see that the majority of p-value I would like to see less than 0.05, with some in the borderline 0.058, 0.055. So the leave one out analysis was conducted to identify whether any single study had a significant impact on the pooled results. The results shows that exclusion of any single study does not substantially change the overall impact. So most exclusion symptoms, so which suggest the robustness of our results. Based upon the leave one out analysis, our conclusion is that as a diagnostic sensitivity check, we look at whether the pooled estimate shifts a lot or losses or gains statistical significance when one study is removed. The sensitivity analysis shows that excluding any single study does not substantially change the pooled effect. A few exclusions yield a borderline p-value, like p-value 0.05, 0.08, as we can see here, 0.058, 0.055, but the direction and the magnitude of effect remain consistent. This indicates that the meta-analysis results are robust and not driven by a single influential study. So based upon this leave one out analysis, we can make this conclusion and to ensure the robustness of our analysis. Different from leave one out analysis, another type of sensitivity analysis is trim and fill method for publication bias. The purpose of trim and fill methods for publication bias is to detect and adjust for publication bias in meta-analysis. The steps consist of the following three. First, the trim, identify asymmetry in the follow plot, which means we consider like missing studies, and then we fill imputed missing studies to restore asymmetry. The final step is to recalculate the pooled effect with observed and imputed studies. How to interpret the results from the trim and fill method for publication bias? If adjusted effect is almost identical or similar to the original effect, we can conclude robust. If adjusted effect substantially different from the original effect, we may conclude that the results may be biased by missing some important studies. the lower part is the results for the binary odds ratio studies we talked about before with trim and fill method. This study is targeting on study the mesh versus tissue repair for the trauma study. And then the purpose is to look at which way is better, mesh or tissue repair. So we are going to evaluate robustness of results by imputing potentially missing studies due to publication bias. When we say publication bias means we may only include some results favor our hypothesis. We may miss some important studies. So we try to handle missing value by using the trim and fill to do the imputation. Observe the results, which means the original studies. We have the random effects is 0.04, suggests mesh repair lowers the odds compared to tissue repair. Now we are conducting the trim and fill adjustment. We use like a follow plot asymmetry suggested of possible missing studies. We use method field hypothetical studies to restore symmetry, adjusted product odds ratio remained in the protective direction through slightly attended. In this process, findings we found that unlikely robust, but publication bias cannot be fully ruled out. So this is the as a way for us to assess some publication bias, like a follow plot shows asymmetry. Few studies appear in the non-significant region area, like in the white region. Pattern suggests a potential publication bias or small study effects. And then we use the results from an original and trim and fill method, and we get the odds ratio for the original and trim and fill analysis. As we can see here, the results are almost identical without considering like 3 or 4 decimal positions. As we can see, here we have the original meta-analysis. We have trim and fill adjusted results. The heterogeneity odds ratio estimates are the same. So we can interpret both analysis, original metadata analysis and trim and fill metadata analysis yield nearly identical pooled odds ratios. The consistency indicates that the observed protective effect of mesh repair is robust and unlikely to be explained by publication bias. So here we can compare the 2 follow plots, original versus trim and fill. We can see the original follow plot on the left side and the trim and fill imputation in the right side. You keep like a balance. For both original and trim and fill, they both analysis favor mesh repair. Now we are moving to the third analysis is about the sensitivity analysis, which is a subgroup analysis. Subgroup analysis is to explore whether specific study level factors modify the intervention effects. Usually we will conduct a subgroup analysis by say study size, study quality or risk bias, and others. But we should keep in mind that subgroup analysis are exploratory and prone to the false positive, should be pre-specified when possible. overinterpretation can mislead clinical conclusions. Subgroups analysis, as I just said, we should pre-specify moderators, test for interaction, and beware ecological bias. For the study we just mentioned, I conducted a subgroup analysis by the sample size. Yeah, so for the larger sample size and for the smaller sample size, we can say the results are pretty close. For the larger sample size, the port odds ratio is 0.48, and for the small sample size is 0.52, with the compatible 95% confidence interval. And then the both heterogeneity quite different from the original studies. With the larger size, heterogeneity p-value 0.01, and for small sample size is 0.052. So cross the borderline. For this study, we can say the small sample size can impact the publication bias. So we can see for the larger sample size with a moderate heterogeneity. But for the small sample size, we can see they did not show the heterogeneity with p-value 0.052. So we can interpret the effect measures are similar between large and small studies, suggest the results are consistent. But heterogeneity may be an issue from the large sample size studies. So this is the reason why we need to conduct the sample subgroup analysis to estimate size effect and heterogeneity, because we can see for the small sample size, we have enough reason to consider publication bias. Another type of sensitivity including for the real events, for the correlated studies, which means for the longitudinal studies, and also for the multiple outcomes. In recent years, we sometimes consider using Bayesian metadata analysis and network metadata analysis. So this is the method for us to conduct the sensitivity analysis. I would like to have a few minutes for you to ask questions. So now I'm going to wrap up. In summary, when we conduct the analysis, we should follow the PRISM 2020 checklist to report our studies, including protocol, searching, stirring, eligibility, data items, bias assessment, and if possible, we could share analytical code and data. We should be careful to interpret our results, including statistical versus clinical significance, such as absolute risk differences, convert uncertainty with the protection interval, discuss heterogeneity resources. And I strongly suggest, if possible, we should conduct some sensitivity analysis. When we conduct metadata analysis, we should be aware of some pitfalls, maximum adjusted or unadjusted effects, double counting arms, inadequate handling of multi-arm trials, and also we should, for the post-hoc subgroup analysis, be careful about the heterogeneity with I-square. Okay, that's my introduction to metadata analysis. Thank you for your attention. Now questions.
Thank you, Zugui. Are there any questions? Yeah, I liked your comment about mixing adjusted and unadjusted. It never occurred to me that you could possibly use, or even by accident, some adjusted odds ratios or hazard ratios. I always assumed that meta-analyses were done on the basic unadjusted summary statistics or summary data.
Yeah, so this is a very good point. We need to be careful if we missing adjusted or unadjusted.
Hi, Zugui.
Yes.
My question was kind of similar. So when we are looking at these different studies and pulling together these estimates, so in the adjusted one, some studies might be adjusting for one set of variable and the other study might be adjusting for very different set of variables. And so many of them might be also common variables, but there might be different on what different studies actually adjust for in their analysis. How is that going to impact the analysis? That's a very naive question.
Yeah, this question is not naive. This question is very important because when we see like the results from unadjusted, that will be like, for example, for the survival data, we may look at from the Kaplan-Meier curves results that will be like unadjusted. But if we look at adjusted, we should further at the very first step when we collect the data, we should have a column-C adjusted by what type of variables, and then we would like to make sure that the adjusted risk factors compatible among studies. That could be a important resource for the effect size or heterogeneity. Yeah. I think this is important in three types of outcomes: continuous, binary, or survival outcomes.
Thank you. Are there any other comments or questions? If not, thank you very much, Zugui, for the presentation, a very comprehensive discussion of meta-analyses. Thank you.
Thank you.
Thank you, Zugui. This is really helpful and very good presentation.